Assalamu alaikum. Welcome to lecture 8 on electric circuit analysis 2. I'm Dr. Khuram Naveed and I'm going to be your instructor in this lecture. So in this lecture we will continue with AC power analysis. Specifically we will talk about maximum average power transfer in AC circuits. So in a previous course we've already seen that in DC circuits maximum power is transferred when transferred to the load when load resistance RL is equal to Thevenin equivalent of the resistance of the DC circuit. So in this lecture we will find the condition that allows us to deliver maximum power from this circuit to this load, um, and in order to do that we will will first find Thevenin equivalent of the AC circuit. And in chapter 10, we have already learned to find Thevenin equivalent of AC circuits using phasor using phasors. Uh, so um, so once we have this Thevenin equivalent, we will then move to find average power delivered to this load. So in order to find the average power delivered to this load, by this circuit, we first need to find the current flowing through this circuit. And it is important for you to know that this V Thevenin is not exactly the the voltage. Uh, in fact, it is the phasor of the equivalent voltage of this circuit at this on visible on these terminals. And this Z Thevenin is the impedance, equivalent impedance of the circuit, while I is also the phasor of the current that is flowing through the circuit, right? And ZL is the load impedance. So once we have this equivalent circuit, we can write an expression for this phasor of current, and that is this one. And since Z Thevenin has both resistive and reactive parts, and similarly ZL also has a resistive and reactive part, so we can replace these values of Z Thevenin and ZL uh, in this expression to find an expanded version of this expression. And so once we have this expression for current in terms of Z Thevenin and Z load, we can then uh, move to find maximum, right? In fact, the average power delivered to this load by this circuit, right? So once we put that expression in this formula, we find this average power delivered uh, to the load. Um, so in order to obtain this expression, we first rewrite the phasor of current in this way, where we combine the real parts and imaginary parts to make it a complex number, and then we compute its magnitude squared. And when we compute a magnitude squared, we basically multiply a complex number with its conjugate. So when we multiply V Thevenin with its conjugate, we end up with magnitude squared of V Thevenin. And when we multiply this complex number with its conjugate, we end up with uh, this expression, and that is because you can think of it as a plus b. This is a and this is b multiplied with a minus b. This is again a and this is again b, but this has a different sign. So a plus b into a minus b are written as a square minus b square. So here, as you can see, this is a square and this is b square, right? So since j square is equal to -1, we can um, write it in this way, because this is supposed to be the magnitude, and it should not have this j, right? So once we have this expression for magnitude squared of capital I, we can then put this expression in this formula to get this particular expression for average power delivered to the load by the AC circuit. So once we have this expression, we can then move to find maximum power delivered to the load. So in order to find the maxima for this power, we need to take the derivative of this power and put it equal to 0. That is because at this maximum value, the derivative is equal to 0. So that means if we want to find the maximum value for this um, power, then we need to compute its partial derivatives with respect to the reactive part of the load and the resistive part of the load, and then we need to put these derivatives equal to 0. And why we are taking derivatives with respect to a reactive part of the load and resistive part of the load? Because we want to find a condition for load that allows us to deliver maximum power to the load, right? So um, so let's start by taking partial derivative of this average power with respect to this reactive part of the load. So so when we so suppose we have this function y that has a numerator and a denominator. So if we want to take its derivative, we uh, we we write the denominator unchanged, and then we multiply it with the derivative of the numerator, right? And then we in the we um, write the numerator as it is, and we multiply it with um, the derivative of the denominator, and we subtract this part from this part, right? And we take square of the numerator, sorry, denominator, right? So so we will use this formula to compute partial derivative of this function. Remember, we want to compute this partial derivative with respect to uh, this quantity xl. Since the numerator does not have this quantity, so it means this d over d, this particular derivative of the numerator will be 0. That means this part will be 0, right? And we will um, so so we only have this part in the numerator of the derivative, as you can see here. So in this part, when we will write u as it is, that is the numerator, which is v Thevenin squared RL by 2. So we will write this part as it is, and we will take derivative of the denominator, and denominator, as you can see, has two parts. um, so this particular term does not have xl in it, so this term will again be 0 when we take derivative with respect to xl, and this part, since it has xl, it will have some non-zero derivative, and that non-zero derivative is 2 into x Thevenin plus xl. So when we write this part here, so this 2 will be cancelled by the 2 that is dividing this numerator. So we will end up with this term in the numerator, and in the denominator we only take the square of the denominator. So we have this square term, right? So when we set this partial derivative with respect to xl to 0, we can see that this term will be cancelled because of the cross multiplication, right? So we will have this expression and rather this equation where x Thevenin plus xl is equal to 0, and from here we can find this condition for xl that allows maximum power to be delivered to the load, right? Right. So once we have this condition, we can now move to find a condition for uh, RL. So in order to find condition for maximum power delivered to the load with respect to RL, we need to take a partial derivative of this power with respect to RL. So in this case, we have the numerator that is dependent on RL, and we also have a denominator that has also RL in it. So this means in this case we when we use this formula we will have this part as well as this part in the numerator, as you can see here. So and we take the derivative of the denominator, sorry, we take the square of the denominator. So right, so let's see how we end up here, right? So when we first we need to take we need to write the denominator as it is, so which we have done here, and we need to take the derivative of the numerator. So here in the numerator we have RL, which will vanish when we take derivative, and we will have V Thevenin squared, V Thevenin magnitude squared divided by 2. So we write this V Thevenin magnitude squared divided by 2 here, and then we will move to this term, and so here we write the numerator as it is. So we write V Thevenin squared RL divided by 2 as it is, and we take derivative of the denominator with respect to RL. So this term, since it does not have any RL term, will vanish because of the derivative, and this term will have some non-zero derivative, and that is 2 into R Thevenin plus RL. So once we write this 2 into R Thevenin into RL, and you must remember we also have this term here, because V Thevenin is also here, and in this term we can take V Thevenin out. So I've taken V Thevenin out, and after some right, so we also have this and we will take square of the denominator, and this 2 is the this particular 2 that is dividing the numerator here, right? So so this term will cancel because of the cross multiplication, this and this part of the numerator will also be cancelled because of the cross multiplication. So we have final this term that is equal to 0. So from here we can find a condition for RL. So in order to do that, we must we let us expand this term and this term. So we take this term on the other side and we expand these two terms, and so here as you can see this particular term and this particular term will cancel each other, and so and because we need to subtract RL squared from the 2RL squared, we will have a negative of RL squared equal to minus R Thevenin squared, because we take this R Thevenin on the other side as well, and minus x Thevenin plus xl whole squared. So from this expression we can find a condition for RL, that is this one. But we already know that the XL is equal to must be equal to minus x Thevenin for maximum average power transfer. We have already seen this in we have already find this condition in this part of the lecture. So let us put this condition in this condition for RL, because this RL is dependent on XL. So we already know what XL should be for maximum power transfer. So let us put that value of XL in this expression, and so we will see that eventually we will find out that load resistance should be equal to the equivalent of the Thevenin equivalent resistance of the AC circuit. So we have these two conditions. So first one is, in fact, we have these two conditions both on this slide, that XL should be equal to negative of the Thevenin equivalent reactance of the AC circuit, and RL should be equal to Thevenin equivalent resistance of the AC circuit. So that allows us to write the load that is required to draw maximum power from the AC circuit, and that load is R Thevenin plus, in fact, R Thevenin minus J X Thevenin. So once we have these conditions, we can then move to find maximum power delivered by the AC circuit to the load. So in this previous part of this lecture up till now, we have found these conditions which allow us to deliver maximum power to the load. But now we will find the actual maximum power that a circuit can deliver to the load. So when we put these values in this expression for average power, we will find that maximum power that an AC circuit can deliver to the load is magnitude square of the V Thevenin divided by R Thevenin, 8 into R Thevenin. Right, so what if we have a load that only has a resistive part and it does not have a reactive part? So in that case, this XL will vanish. So we will have this expression for the load, and that essentially means that the load resistance should be equal to the magnitude of the equivalent Thevenin equivalent impedance of the an AC circuit, um, if we have a purely resistive load. So now let's look at an example. So this is an AC circuit, and we want to find the load impedance ZL that maximizes the average power drawn from the circuit, that is 11 figure that is given in figure 11.8, which is this one, and then we also want to find maximum average power. So in order to find the load impedance ZL that maximizes the average power drawn from the circuit, we first need to find the Thevenin equivalent of this circuit. So in order to do that, we replace this voltage source with a short circuit, and we find the Thevenin equivalent impedance from these terminals, and then we also um, find Thevenin equivalent voltage on these terminals, um, and uh, uh, and this voltage is basically the voltage across this network of circuit elements. So this voltage can be found using the voltage divider. So we have this Z Thevenin, and we have this V Thevenin. Um, so once we have these two, we can write we can write an expression for the impedance ZL that maximizes average power, and that is the complex conjugate uh, of the Z Thevenin. And so Z Thevenin is this one. So the load impedance that maximizes average power should be 2.933 minus J 4.467, and maximum power can be computed by using this expression where we R Thevenin is this part of the Z Thevenin, and so we can put this value here, and we can put the value of the magnitude of the V Thevenin, which is um, 7.45, and we can find the maximum power that this circuit can deliver to this load. Alright, so that's the end of the lecture. I hope you have understood the concepts in this lecture. Goodbye.